There's a one may be tempted to sleep in a bit.
Yeah, after the conference dinner. Yeah.
Okay. Is there a way to see the
The auditorium?
participants?
Yeah, probably. Let me check. O Zoom daqui tem, ele vê
Oh, there we go.
imagem da plateia? Sim. Mas tá ligada? Jonathan, there is this camera here that sees the audience from back.
Okay, I can see
Are
the
you
back,
see?
but I guess so I won't be able to see. I guess the difficulty is I don't see people's expressions, so I don't see whether people have
Yeah.
lost interest or are still
Sorry.
with me or not. Um,
Yeah. Well, I can try to help with that.
okay, so maybe if you can,
I can
maybe what
join
would be
Zoom.
helpful then. Sorry.
I can join Zoom from my device, and then I can put you watching from. I'm gonna show you. Do you do you have Zoom there? So you can put it. He's sitting here.
Um, I don't. Maybe the best solution is if oh, I can. Yeah, it's very small. So maybe the best solution is if you or other people in the audience could ask questions during, especially clarifying questions during the talk, just so that we're able to kind of keep a connection. Because I think otherwise, I don't have any idea if, for all I know, the
Okay.
entire audience has stopped listening, and I don't have a good sense of that. So if
Okay.
maybe people could be a bit more vocal than usual in terms of asking questions and prodding me if I say
Well,
something which
the
is
we can try that, Jonathan. I can when
okay.
people raise their hand, I can give them their microphones, but
Okay.
with the problem is that you can't hear immediately when someone starts talking. So,
Right.
but
Right.
here on the camera you can see a little bit of who is here, right?
If I stop sharing, I could, but I don't want to do that. So I can
Okay.
pause share. No. Okay.
If you show video participants, there is Giorgio Torieri.
Yes. Okay. Pin. Oh, there we go. That's a bit better. Okay.
So, yes. Is that okay, Jonathan?
Yeah, that's great. Thank you.
So, let's start with our morning chat session with Jonathan Oppenheim. That's going to talk about renormalization of a post-quantum theory of classical gravity. Thank you, Jonathan.
Great. Great. So yeah, thanks people for coming, especially first thing in the morning and after the conference dinner. And I'm sorry I'm not there in person. I'm going to talk about some joint work with Andre Gruca, Tim Morris, and some of my students, Mohammed Sajid, Andrea Russo, Zach Davies, Barbara Soda, Carlos Baracchieri, Emmanuel Panella, and also my colleague Andrew Ponson. So mostly I will talk about the PRX, the recent PRX paper, which introduces this post-quantum theory of classical gravity. I'll also be talking about this Nature Communications paper, which talks about the experiments that we can do in order to test the quantum versus the classical nature of gravity. And I will also, for this audience, especially try to talk about the renormalizability of the theory. And so I will, because of that, I'll introduce the path integral approach to the theory, and I will talk about why the theory is at least formally renormalizable. and we have some, so that's a paper on the archive, and we have some further works, which I think even the indication that we have initially is that also if we include matter, then the gravitational sector at least will be renormalizable. And so that's the main results I want to talk about. And I would definitely appreciate clarifying questions during the talk, because this is going to combine a number of different fields: quantum field theory, classical stochastic dynamics, and GR. And so it's, and as well, open quantum systems. So it's a kind of a set of topics which almost nobody fully has a background in. And so it's going to be very natural that people will have questions. So please just ask at any point. Good. So let me just start by phrasing the question. We have two frameworks in physics. We have quantum mechanics, and the evolution of a density matrix is given by the Hamilton's equation. So I'm just trying to see if people can see my cursor. There we go. Can people see the pointer?
Yes.
Yeah, okay. So we have a density matrix sigma, which will evolve according to a Hamiltonian, according to Heisenberg's equation. And then in classical mechanics, we have a point in phase space. So a system will be represented by a point in phase space. And then the evolution of the probability density rho is going to be given by the Liouville equation, which has a very similar form to the Heisenberg equation. And so you can ask the question, can we combine these two frameworks? People have played with other generalizations of quantum mechanics and classical mechanics with, I think, very little success, because most of those theories tend to have problems, or frameworks tend to have problems. So what I want to ask is a simpler question, which is just, given that we only have these two frameworks for physics, can we combine them in a consistent way? And we often combine them in one direction, namely we have a classical system which can influence a quantum system. So an example is a particle in a potential, or say the double slit experiment, where the walls of the screen of the experiment we model classically, and the particles we model quantumly. We often consider those sorts of combining of classical and quantum systems, but what I'm asking is whether we can also deal with the back reaction, namely we have a quantum system which back reacts onto the classical system, and I want to ask the question, can we treat that in a mathematically consistent way? The motivation comes partly just practically because there are often systems which we want to treat classically, even though they interact with a quantum system. But I'm also motivated by gravity. And I'm actually, you could be motivated either because you want to ask whether space-time is fundamentally classical or quantum. You can also ask the question whether, from an effective theory point of view, we can consider consistent dynamics where the gravitational background, the space-time background, we consider to be classical and allow for the quantum fields to back react on that. So I'm interested in both these considerations, and I'm also not always, I don't think it's very clear whether there's actually a difference between the two. And that is because I only know how to do physics if I have a classical background structure. I only know how to do physics if I start with an initial time slice, and I have to know that that is a spatial slice. And so I need to know the metric in that space-time in order to even pose the initial value problem. And then when I define the commutators, I say that, two fields at point X and Y commute if they're space-like separated. So I need to know the causal structure before I can even define my quantum field theory. So just in terms of how we do physics, I think we're kind of pushed towards considering such a hybrid approach. From a fundamental point of view, I also think that it's important to recognize that gravity is fundamentally different from the forces of nature. In fact, gravity is not a force. I just free fall. Gravity, fields and point particles and test masses just free fall in gravity. No force is acting on them. And that's different to the actual forces, which none of them, although you can sometimes have a geometric description of the forces of nature, none of them can universally be represented in terms of a geometry. So it's only gravity that can be described in terms of a universal geometry in which all the quantum fields and forces live. So I often, have this picture here where we have space-time as this background arena, and inside space-time in this background arena, we have gauge fields and exchange of gauge particles in order to represent the forces, the quantum forces of nature, but space-time itself may or may not be quantum. And there's reasons to imagine that it may not be quantum, and one of them is, for example, that if you try and quantize gravity, you get the Wheeler-DeWitt equation, which is very difficult to deal with, to say the least. It seems that our quantum state doesn't evolve. And this largely has to do with the fact that gravity is not a gauge theory. So the symmetry transformation of gravity is diffeomorphisms. They move the points x, they move space-time points. That's the active part of the active transformation that corresponds to a coordinate transformation. And so the symmetry of the local symmetry of gravity is diffeomorphisms, and that is not a gauge transformation. A gauge transformation acts on internal degrees of freedom. So if I have a field phi of x, the gauge transformation acts on psi, whereas at the point x, whereas diffeomorphisms move the point x. So gravity is not a gauge theory. Therefore, it's unclear, I think, whether we should actually be quantizing it. Are there any questions at this point?
No.
Okay. Either the talk is clear, or I haven't said enough, or people are still recovering from the conference dinner. Good. So let me give you some further motivation. I don't, know if space-time is classical or quantum, but if space-time is classical, then it would have a number of interesting consequences, which to me are kind of attractive. So one is that the theory, at least in the gravity sector, is formally renormalizable, whereas perturbative quantum gravity is not renormalizable. When I observe what's happening with my colleagues, say in string theory or other areas, other areas of quantum gravity tackle the black hole information problem, it feels to me like one gets a number of paradoxes, and those are resolved if black holes destroy information, and this happens very naturally in these classical quantum theories. And so the black hole information problem is one motivation for studying this classical quantum theory. You also don't need the Born rule or the measurement postulate, and that is because if I have a quantum system interacting with a classical system, then the quantum system necessarily localizes. You necessarily get collapses and probabilities if a quantum system interacts with a classical system. So you don't need the measurement postulate, and that's one motivation, I think, to consider such theories. Also, it just happens to be that we can actually experimentally test this theory. So it has a number of signatures which we can test. And I'll talk about one of them called the decoherence versus diffusion trade-off. But there's also this gravitationally mediated entanglement, which has been proposed by Bose and also Marletto and Vedral. And so this proposal is experimentally testable. Now, for much of the debate, there was, I think, for much of the history of this question of whether space-time could be classical, there was a lot of debate back and forth and various arguments. And I don't want to go through those because I think it's now established that you can, in fact, find consistent theories of classical systems coupled to quantum ones. So examples go back to the mid-90s, Blanchard and Jadek, Diossi, Poulin in 2017, and then even some models of Newtonian gravity, so Diossi and Tilloy and Caffey, Taylor, Milborn. So there are some simple examples already of classical systems which can consistently interact with quantum systems. And therefore, I think we can now consider whether gravity can be a part of this. I want to say that I will not be considering something called the semi-classical Einstein's equation, which is where you use expectation values. It's well known that that's ruled out by a number of considerations, including experiment and a breakdown of the density matrix. So I will not be considering the semi-classical Einstein equation, which breaks down. I will only be considering, in some sense, linear theories. So the plan for the talk is I'm going to discuss the most general form of the dynamics, mostly through the path integral, but I will also show a very simple example. Then I will discuss this decoherence versus diffusion trade-off, which allows us to test the quantum nature of gravity. And then I will talk about why it's renormalizable without ghosts. If I have time, I'll talk about these anomalous contributions to the metric which occur and which may be an alternative explanation to dark energy and dark matter, but we can go, at a kind of a slow pace. Okay, so let's talk about the general form of the dynamics. And so remember, we have the Heisenberg equation, which is just d sigma dt is given by the commutator with the Hamiltonian, and it formally looks like, in classical mechanics, the Poisson bracket with the Hamiltonian. And so this is just, we're not going to do the semi-classical equations, but we're going to, the key point, sorry, about why the semi-classical equations don't work is because if you take the expectation value of the stress energy tensor, you are kind of throwing away correlations between the classical system and the quantum system. And so we want to keep the correlations between the gravitational field and the matter degrees of freedom. And in order to do that, we need to consider a joint a probability density, which is like a joint system of the a joint state, sorry, of the classical system and the quantum system. So, for example, I have a classical particle, which is represented by a point in phase space. I have a quantum system, which is represented, say, by a two-level system, by a density matrix. And so we can represent this in terms of a probability over phase space. And given that I live at a particular point in phase space, we have a density matrix in the Hilbert space. So, given that I live at a particular point in phase space, I have a probability of the quantum system being in the zero state, probability of the quantum system being in the one state, and then the coherences. So that's how we represent a classical quantum system. It's just a joint system of the classical system and the quantum system. And it has to, because this state of the system gives us the probabilities of being at a particular point in phase space and being having a particular state in the Hilbert space. It has to be positive because probabilities are positive, and it has to be normalized because probabilities are normalized. So we have to have this object, this classical quantum object, which is here, has to be positive, and it has to have a normalization of 1, meaning that if we take the trace of it over the Hilbert space and integrate over phase space, it has to normalize to 1. And here you see how I've represented the classical quantum state. It has a probability rho of being at a particular point in phase space, Q and P, and then given that we live in that point in phase space, it has a density matrix sigma. Is that clear how I'm representing joint states, one of which is classical and one of which is quantum?
Yes. Everyone is nodding.
Everyone's nodding. Okay. Okay, and so it's now fairly straightforward to derive the most general form of the dynamics, because we just say that the dynamics must preserve the state space. So it must take positive states to positive states. It must preserve the norm. It must do so even if I only act on, Anupam?
So, Jonathan, yes, nice. So just to clarify, so this is your assumption which you're making here. It's an added assumption which you are, am I correct to understand?
I don't think it's an assumption in the sense that I don't think I think the only assumption is that we are going to represent quantum systems and classical systems in the same way as we represent them normally in classical mechanics and quantum mechanics. So I don't think once you say, okay, I'm going to represent states in terms of rays in a Hilbert space, then I think and we're going to represent the classical system by a point in phase space. I don't think you have any choice. Because you have to preserve that state space, so your dynamics has to be completely positive. The only assumption I will end up making a bit later, and I don't make, the dynamics actually has the same form regardless of whether I make this assumption. But I will, if I'm interested in a fundamental theory, then I'm going to assume that the dynamics is Markovian, meaning there's no hidden memory. And that's a natural one if I have a fundamental theory. But I think in terms of how I represent the state space and that the dynamics has to preserve that state space and be linear, I don't think I would not call that an assumption, although I think one must be very explicit about stating, those conditions.
Thanks.
Okay. And maybe you're asking that because there are, I think, many different forms of hybrid dynamics that people have proposed over the years, and most of them have not had the property of being completely positive. And in my view, that's fine if it's not a fundamental theory. You can have negative probabilities if you don't, but if you're not trying to have a fundamental theory. But if you believe that probabilities are positive, then I think you are forced into the master equation and or at least the master equation that we have derived. So what I want to do is just give a simple example, and then I'm going to talk about the path integrals, because I think people like often, seeing the different path integrals. And I think I spent a lot of time, looking formally at how classical mechanics and quantum mechanics are similar, and it's nice to see everything kind of sitting in a very similar formal framework. And I think one gets a lot of insight into both classical mechanics, quantum mechanics, and the combination. So that's why I'll go through the different path integrals. But let me first just give a little simple example so that people can see how a Stern-Gerlach works. So a Stern-Gerlach, this is just a very simple example. We have a free particle. So the Hamiltonian is p squared over 2m for the free particle, which lives in phase space, q and p. And then we have a magnetic field. Here, D1 is the strength of the magnetic field. So it tells you the force of the back reaction, gives you the force. So here we just have a linear potential. And then this magnetic field is coupling to the spin, sigma. So what this will do is just, it will measure the spin. So the free particle, especially P, for example, will get a force which depends on the spin of the particle. And go up or down depending on whether it's spin up or spin down. And that's a simple example of a classical system interacting with a quantum system. Now, in order for the dynamics to be completely positive and trace preserving, what we find is that there has to be, necessarily, there has to be stochastic evolution in the classical phase space. And there has to be, I wouldn't call it decoherence, but the quantum system, if you ignore the classical system, then the quantum system appears to decohere. So here's, let's imagine that we start off our quantum system in a superposition of being up and down, then in the plus state, then it will either collapse into the 0 state or collapse into the 1 state. And when it does that, the classical particle will move into one direction or the other. Initially, you will not know whether the particle is spin up or spin down because of the stochastic kicks that the classical particle is feeling. So initially, when you look at the classical particle, you don't know if it's going up or down. So you don't know whether the particle is spin up or spin down. But eventually, you learn that the particle is spin up or spin down. One of these paths is chosen. Oops. One of these paths is chosen. And if you saturate this, so let me give you the full dynamics. So the full dynamics is given by, you have the quantum system, which interacts normally by the Heisenberg commutator. You have the classical system, which evolves as you would by the Poisson bracket. But because you have an operator ordering ambiguity, you take both orderings and take the average. And then in order for the dynamics to be completely positive, trace preserving, you need to have diffusion. This is this D term, D2 term in the classical system, and you need to have decoherence in the quantum system. And in order for the dynamics to be consistent, in other words, be completely positive and norm preserving, it needs to satisfy this trade-off, meaning that the diffusion coefficient D2 and the decoherence coupling D0 have to be larger than the force squared. So that's this trade-off that this that the combined hybrid dynamics has to satisfy, and it's what we're going to use in experiment. And what is somewhat remarkable, so here's the dynamics again, what is somewhat remarkable is that if you saturate this trade-off, what happens is that the quantum state stays pure, conditioned on the classical system. And so even though you have what appears to be decoherence, it's not actually decohering. What's actually happening is that the quantum state collapses to the 0 or the 1 state, but it does so, it stays pure the whole time. So it evolves, it just stays on the surface of the block sphere here and just evolves to the 0 or the 1 state, but it does so staying pure the whole time. Are there questions about the simple model? Because I think a lot of things could be understood in the simple model.
Apparently not.
Okay. I hope I haven't lost people then.
I'm telling you about the time on chats. You had 20 minutes.
Okay. So let me now talk about path integral. So if you've lost if you've lost the thread, or if I've lost you, then now we're going to start afresh, and you can rejoin. I hope you do. And so what I'm going to talk about are different path integrals. So I think you can see nicely why quantum path integrals and classical path integrals, how they're related. And this is really at the heart of why gravity in this framework is renormalizable. And so here is the quantum path integral you're familiar with. We have some initial state, psi I, it goes to some final state, phi f, and we integrate over e to the I times the action, and this gives us an amplitude of going from some initial state to some final state. So the quantum path integral is computing an amplitude. Now we can also use the path integral formalism to compute a probability or even a density matrix. So in other words, we want to compute not just one amplitude, but we want to consider a whole density matrix. So we have we double the number of degrees of freedom. We have a bra field and a ket field. So we call these phi plus and phi minus. And this allows us to compute the elements of a density matrix, not just amplitudes of a wave function. So for the density matrix, we have two path integrals. And we integrate over the bra field, psi plus, and the ket field, psi minus. They have opposite phase because one is the complex conjugate of the other, and this allows us to compute the density matrix. So you can see here that we are computing the density matrix in this path integral formalism. Questions about the quantum mechanics path integral for density matrices?
No, most of us are familiar.
Okay, good. Yeah, so you'd either be familiar with it if sometimes called the Feynman-Vernon path integral, so you can introduce, so Feynman and Vernon, for example, introduce this decoherence functional, and so if you have some coupling between the bra and the ket field, then you have decoherence. You can see that this looks a bit like a Lindblad equation. And if I can rewrite it like this, you can see that they have a decoherence term, which effectively decoheres the state when the bra field is very different to the ket field. So this will decohere the density matrix with a strength given by D0, and it will do so and cause the density matrix to become diagonal in phi. It's sometimes called Schwinger-Keldysh. It's closely related to that if you're familiar with that formalism. Next, we have classical mechanics. Classical mechanics, at least the deterministic theory, has the most boring path integral imaginable because at every point you have to satisfy Hamilton's equation. And so here you have a delta function around Hamilton's equation and you integrate over all paths, but there's only one path that's allowed. And so you just have a single path. So here we want to compute the probability that if we start in a particular, or at least the probability density, that if we start at a particular point in phase space, qi, pi, we end up at a final point in phase space, qf, pf. If, however, I add noise, then I get a genuine path integral where I'm actually summing over different paths. So for example, in Brownian motion, I start off at some initial point. And now there's a whole bunch of different paths I can take. So here is the path integral for Brownian motion. It's called an Onsager-Matchloop path integral. This was introduced, I think first, actually, this particular one for Brownian motion can be found in the book of Feynman and Hibbs. And so you can look at this path integral here, and you can see that what's happening is that if, there's the path in which f equals ma is exact, and that's the dominant path. But I'm also allowed fluctuations around f equals ma. And so those are the paths which have stochastic kicks, as in Brownian motion, and they're suppressed. This is kind of a Gaussian suppression, but they're allowed. So I have these kicks around f equals ma. They're suppressed the further they get from f equals ma, and they're suppressed exponentially. And the amount they're suppressed is given by this diffusion coefficient d2. Notice also that there's additional degrees of freedom now because in some sense, if I'm free to choose the acceleration independently of the position and velocity because of these stochastic kicks. So this is the path integral for Brownian motion. Any questions about Brownian motion?
Nope.
Okay, so notice that Brownian motion, and this will become important for gravity, Brownian motion is like an equation of motion squared. So the action is just f equals ma squared, but you can also consider any kind of Euler-Lagrange equation, you square it, and then if you satisfy the Euler-Lagrange equation, that's the dominant path, but you allow fluctuations around the Euler-Lagrange equation, and that smells very similar to what happens in quantum theory, right? We have, the path which extremizes the action and satisfies the Euler-Lagrange equation is the dominant one, but in quantum mechanics, you get these other paths. And likewise here in this classical Brownian motion case, the dominant path is the one given by the Euler-Lagrange equation, but you allow fluctuations around it. Okay, so that is these classical path integrals, and you won't be surprised to maybe hear what you might do with gravity or try to do, which is that if the action is given by an equation of motion squared, you could take Einstein's equation, say here in the vacuum, and contract it with itself, so the equivalent of squaring, and that will be the path integral for gravity. So it's a stochastic path integral for gravity. I'm going to just say this again. How am I for time now?
12 minutes.
Okay. What I will just say, and I won't say it won't be too long. I'll just say that here so this is this kind of formal similarity I like to show, which is that we have the path integral for quantum mechanics. Here is the Feynman-Vernon term that causes decoherence. We have the path integral for classical mechanics, and here we suppress paths away from Euler-Lagrange equation or Hamilton's equation, and then together we can combine them into one path integral, which effectively combines classical systems and quantum systems. And I'm just going to flash it here and go on, but it's important to see that you have both. You have the decoherence term D0, and you have the diffusion term given by D2, which causes diffusion. So you need to have both those things, and that is going to be the way we're going to test this theory experimentally. So yeah, let's talk about that. So the idea is as follows. Let's imagine that we have a classical space-time, so a classical gravitational field. So now I'm talking about the experiments, and again, um, if I lost you during the previous part of the talk, you can tune in again here, because this is about the experiment and how we can test the quantum nature of gravity. We imagine we have a superposition of a massive object, like say, a 1 millimeter gold atom, gold sphere, or an electron is in a superposition of being here and there. We imagine space-time is classical. That means we can measure the gravitational field to arbitrary accuracy because it's classical. We can do so without disturbing it. And if we do so, then we're going to learn whether the particle is here or there. And that's because the particle will have its gravitational field, and it'll have a different gravitational field depending on whether the particle is here or there. And if we can measure the gravitational field to arbitrary accuracy, then we can determine whether the particle is here or there. And that would contradict the fact that we have a superposition of being here and there, and it would violate the uncertainty principle because we could use the gravitational field to measure whether the particle is here or there, and based on that, we could know both the position and the momentum of the particle. Are there questions about this kind of thought experiment?
Nope.
Okay. So let's see what happens. Maybe you want to think about how it is that we avoid this paradox. The paradox, again, is that if the gravitational field is classical, then we'll be able to determine whether the particle is here or there, and then we won't be able to have superpositions, yet we witness superposition. So that's the paradox, or the apparent paradox, and it's resolved because if the gravitational field has a stochastic component, so it has stochastic fluctuations, then measuring the gravitational field doesn't uniquely determine where the particle is. So we measure the gravitational field, we can measure it to arbitrary accuracy, but we can't use it to determine exactly whether the particle is here or there. But if we wait long enough and we keep measuring the gravitational field, we don't actually have to measure it, but we can imagine that we do. Then eventually, if we were to measure it, we would somehow learn whether the particle was here or there. And eventually we learn that the particle is there. And so eventually we are collapsing the particle to being there. So that's the physical intuition behind why you need a trade-off. You need to have stochasticity, otherwise you would violate the uncertainty principle, and you wouldn't be able to see, or you wouldn't be able to see superpositions of particles. And so we see that we have both this decoherence and this diffusion. The particle has to eventually decohere and collapse to being here or there, and you need to have stochastic contributions to the gravitational field. Another related thought experiment, essentially the same, is that I have a double slit experiment. I use a massive particle like an electron. I perform the two-slit experiment. I witness a interference pattern. That means I know that I have a certain coherence and that the particle, in some sense, I can, because there's an interference pattern, it should be that I cannot otherwise determine whether the particle went through slit 1 or slit 2. And yet, if the gravitational field is classical, I should be able to determine whether the particle went through slit 1 or slit 2. And so the only way that I can avoid that is, well, because of this, the reason that this doesn't result in a paradox is because if space-time is stochastic, then I cannot use the gravitational field to determine which slit the particle went through. And so I will not have a contradiction. And so what this means is that I can...
There is a question now.
Oh, good. Yes?
Dane Daniels.
Hi, Jonathan. So I just have a question about what you mean by stochastic. So normally, when I think of a classical probability distribution or a probability distribution on a classical system, it reflects my degree of knowledge or ignorance about the system. So if I have
Right.
if I were to make a perfect measurement, which would be in principle possible for a an ordinary classical system, then I no longer have a probability distribution, or rather, I have, you know, now have a point in phase space, and classically that's fine. So I'm not sure what, I guess I'm curious in what sense is this, or in what sense are you using the word stochastic? Because from that point of view, I guess I would have had I was under the impression that I would still be able to then make a perfect measurement of the gravitational field that would update my degree of knowledge to be, in principle, arbitrarily good. And I don't see how that would save me from the kind of issues that you're saying that it would save me from.
Right. So that is a great question, and I think that there's an open question which is corresponding to that, which I can will try and state as follows. So let's go back to this double slit experiment here. If I can, you know, what we're saying is that if you measure the gravitational field, you cannot determine which slit the particle went through. That has to be the case in order to not contradict quantum mechanics. Now you can say, is there a hidden, does this theory have a hidden environment? That's maybe a way of interpreting your question. Is there some underlying hidden degrees of freedom which I'm missing? And so even though this theory looks stochastic, it's not fundamentally stochastic. There's a hidden environment. Or another way of saying it in the purely quantum case is, if we think we have a fundamentally Lindbladian theory, well, can't we always just imagine that there's an environment, and we're just ignoring that environment? And so the question is, could there be a hidden environment behind this theory? Is that a restating of your question?
Yeah, I think, in order to resolve these paradoxes, it sounds like perhaps you would need a hidden environment. But yeah, that's essentially the idea.
I think, yeah, and so I think I would say that the opposite, that I believe that in order to not have a paradox, there cannot be a hidden environment. So, because, you know, what seems to be happening here is you don't get a contradiction with physics because you don't get a contradiction with physics because if you measure the space-time, you're not able to determine which slit the particle went through. Now, you might imagine that there is some other degree of freedom you could use to determine which slit, which you could then measure. That's a hidden environment. And if that would let you determine which slit the particle went through, then you would also be violating quantum mechanics. So, you know, even if in principle you could determine which slit the particle went through, then clearly you cannot have an interference pattern. And so that mediates away from the idea that there is a hidden environment. Now, I don't have a proof of that, but to me, it's attractive in the sense that it indicates a fundamental irreversibility. And I like that because it helps me both resolve the measurement problem in quantum mechanics, because you have fundamental irreversibility, and it also helps me resolve the black hole information problem. But most physicists don't like it because for them, physics should be predictable. And so it kind of makes us uncomfortable. But yet that's what we seem to see here. I see there's a few more hands up.
You have
I
5
can't quite
minutes,
resolve.
Jonathan. You can choose to answer it now or at the end.
If people want to just ask, if they would prefer to wait to the end, I'll wait to the end. If they want to ask
Your
now,
choice.
ask now. Okay, let's wait until the end. So we have this trade-off, and the idea is that we can now go and perform experiments to see whether there is sufficient stochasticity in the gravitational field in order to allow us to have a certain level of coherence in double slit experiments. So the idea is that we are going to be doing two kinds of experiments. We do double slit experiments and we do Cavendish experiments, precision Cavendish experiments using quantum technologies and state-of-the-art double slit experiments. These have already been done, and we need to improve them by several orders of magnitude in order to rule out the theory. But the nice thing is that you get a bound no matter what. So if we, for example, what happens is that if you there's this trade-off which says that diffusion has to be very large in order to have a long coherence time. And so if we measure a long coherence time, that means we should see a certain level of noise in Cavendish experiments. And if we don't see that noise, then we've ruled out the theory. So this is falsifiable by seeing, in some sense, less noise than we need in the Cavendish experiment. And you can rule out some simple models at the moment already, but the full relativistic theory is not ruled out. But we also there are various choices that can be made, and so we're still at the moment of trying to understand how many orders of magnitude we still need in order to rule out the theory. So that's the experiment that we're proposing, and it just goes by the name of the decoherence versus diffusion trade-off. And these are some of the bounds we've derived and the models we've ruled out. Good, so renormalizability, just quickly. Do I have any time? Where are we with time?
2 minutes.
2 minutes. So let me just mention the renormalizability. So in quantum mechanics, here is the path integral. In classical mechanics, we have this F equals ma, and notice in the classical path integral that we have higher derivative terms in our action. And when you see these higher derivative terms in the action of Brownian motion, you're not worried. I mean, you see those in Feynman and Hibbs. That's a standard term to have these, Q double dot squared terms. So those are higher derivative terms that we're very used to in classical stochastic dynamics. But in quantum mechanics, there are problems. So in quantum mechanics, if you have a path integral which has Q double dot squared in quantum mechanics, you have something called a ghost. It has negative norm. It suggests there's a problem. There are ways that people try and resolve this. So for example, quadratic gravity, which I think John may have talked about, is a theory of gravity which is renormalizable because it has these higher derivative terms. It has potentially these negative norms or ghosts. There are ways that people like John try and resolve it, for example, by only having small violations of causality. But it potentially spells trouble for such theories. On the other hand, higher derivative terms in the classical degrees of freedom are not a problem because they just represent Brownian motion. So that's the main message in some sense, and that's why the theory is renormalizable. And that's one of the reasons I'm excited about it, because I think you get renormalizability without having, extra dimensions or supersymmetry or anything like that. And so this results something called the Ostrogodsky instability, which is the instability you have if you have higher order derivative terms in the action. So here we have these higher derivative terms, like an R squared term and a Weil curvature term squared. We have non-minimal couplings as well. But they look strange, but they actually make a lot of sense when you think about equations of motion squared. So with that, I'm just going to summarize and mention the open questions, and then we can take questions. So let me just mention the challenges. So what we have shown is that there is a general relativity in quantum field theory. So we can reconcile classical general relativity with quantum field theory. There is a master equation, which is a generalization of a Limbladian, and we can prove that the dynamics is completely positive trace preserving, but we do not know if it's covariant. Likewise, there is a path integral, which is generally covariant, but we do not know if it's completely positive trace preserving, but it is renormalizable. And we think, although this is just preliminary, that it's renormalizable when you include the matter sector, except for some terms which are irrelevant. So it seems to behave well or reasonably well when we add matter. And so those are the tensions which I think still need to be understood. Maybe they're there, maybe they're not. We haven't proven that all these criteria can be satisfied. And so in the end, is space-time classical? I have no idea. The odds I've been given are good, so I'm taking bets at really great odds for me at least. And I think I would put I think the chance that it's because gravity is not a gauge theory, it's much more reasonable to think it could be classical than say anything else. And so I don't know if space-time is classical, but we have these experiments via the diffusion and decoherence trade-off. We don't need the measurement postulate. The theory is renormalizable without ghosts and could explain dark energy and dark matter. And so with that, I'd like to thank you for your attention.
I know there is a lot of questions, but we have just a few minutes.
Okay, thank you for the talk. I have a very fast question. So, from the point of view of the theory, a spin-2 particle would be a quantum particle and would exhibit interference in a two-slit like experiment, or shall we see it as a weak field approximation of Einstein's equations, and so it would be part of the space-time and would behave classically? So a two-field, a massless spin particle, spin-2 particle would behave classically because it's a weak field approximation of Einstein equations, or quantum mechanically because this would be a quantum particle?
I mean, if you treat, I'm not entirely sure I understand the question. So if I have
Sorry. So let me rephrase it. Suppose that
Okay.
you make a gravitational wave with an amplitude small enough such that you, in principle, would treat it quantum mechanically. But still, this is part of the space-time. So the question is whether it would behave classically and exhibit no interference, or quantum mechanically and exhibit interference.
Right. So, I mean, in this theory, the gravitational waves are treated classically. So there is what you're calling a spin-2 particle. There is a tensor mode, so a gravitational wave. There's also a scalar mode, like a scalaron, but classical, because you have additional degrees of freedom because you have these extra fluctuations. So you do get both a scalar and a tensor mode, which is purely classical. Now, I think what you're asking is if I were to add on top of that a quantum spin-2 field, is that what you're asking?
No. What I'm asking is, assume that the gravitational wave is so small that the amplitude is of the order of h bar. And then from the canonical point of view, this is a quantum particle, a spin-2 particle, massless spin-2 particle, and would treat it quantum mechanically. But still, this is a perturbation of the space-time. So as a perturbation of the space-time, this would be classical from your point of view. Is that correct?
That's right. That's correct. So here, the fact that it's small doesn't, the fact that it's small has nothing to do with whether it's quantum or classical. Here, it's still classical.
Okay. We have another question in the audience, then we go to Anupan.
Thanks for the talk. I mean, I find the idea, I like the fact that you introduced it as part of your introduction was the idea that the quantum system back reacts on the detector. It's actually, one of the original papers on quantum gravity from the 30s by Matvei Bronstein basically said that this is the objection to quantizing gravity from the equivalence principle. The fact that because of the fact that the inertial mass and the gravitational mass are equal, the back reaction of the system on the detector is always of the order of quantum gravitational effects. So even if the gravity is fundamentally quantum, an effective theory which includes interaction with the detector, which is never completely classical for this reason, could very well be something that similar to what you're doing. And in the end, so there is what I'm asking is, in the end, you mentioned something about full general covariance of the integral. So does this mean that in your theory, all correlators that you calculate will always be generally covariant? If you calculate like a 4-point function and you go to a non-inertial frame, will it transform according to the general covariance of the frame transformations, or you do not know that yet? Because this
No, they definitely are. covariant. So for example, the 2-point function for the scalar mode goes like 1 over p to the fourth, where p is the 4 momentum. And usually in the quantum case, we would expect it to go like 1 over p squared. And the reason it goes like 1 over p to the fourth is because we're computing a probability, not an amplitude. So it's like the mod squared in some sense of a 2-point function. So they're covariant, but what we haven't proven, for example, we've only proven that the scalar mode, that the 2-point function is positive semi-definite, which it has to be because it's a classical covariance matrix. So we need two things to happen. One is it has to be covariant, and they are, but we also need an additional criteria, which is that the 2-point function has to be positive semi-definite, and we know that for the scalar mode, and we're checking for the tensor mode.
Anupam, try to be fast, so we have another question here in the audience, and let's try to finish it.
Maybe the audience should be given
Okay,
preference.
thank you, Anupam. John Donahue here.
Hi, Jonathan. As
Oh,
I
hi,
said to
John.
you
Good to see you.
in person, when we were having our last conversation, I know how to do matter loops, and they're definitely inconsistent with the action that you have there. So it's not going to be renormalizable with matter loops, just because you don't have the term there. But since then, I've been thinking that I don't see why you don't just allow the usual gravitational terms, the quantum terms in there, and add your diffusion terms to that action, because that would form an interesting test system. They could be the dominant terms, for example, in some gravitational experiments. I don't see that why you just don't allow it to be quantum in the usual way and add these new terms, the ones that don't have a factor of I in there, on top of the usual expressions, and look at the effects of these new terms.
Great. So let me address the first part. So there's a question you're raising, which is if I add matter, then will I get additional couplings because of counter terms, which I didn't have there initially and which would make the theory sick. So for example, would I get, I start off with a real action, which has a minus r squared. If I add matter, do I get a minus I r or a minus I r squared? That's essentially your question, if I understand. Or no, that was your first point you made before you started the question. Is that fair?
Yes, that's correct.
Yeah, and so I think so that's something that is good to worry about, and we've checked for a simple system, and that appears not to happen. And the reason is that you have these right fields, these bra fields, and these ket fields, and the diagrams just cancel. So they come with an opposite sign, and so all the imaginary parts cancel. And so at least to one loop order, we don't see such coupling. So it seems to in fact, it's UV finite even because of those cancellations. So at least at one loop, we don't induce these imaginary couplings. Now the question about could you consider a quantum theory where you add the r squared term? I think that's an interesting proposal. Because if I understand you, it would give you renormalizability, but possibly without ghosts. Is that the motivation behind that?
So if you're working at low energy, I just wouldn't worry about renormalizability. There's some other theory that takes care of renormalizability eventually. But you're looking at low energy effects of gravity.
Right.
You can put the quantum effects in there. The quantum effects are pretty small, as we know. Your diffusion terms might be dominant. So if you just did the standard quantum theory with your terms, you would have an interesting theory that's more consistent than you are presently.
Right. So I think that is a good thing to do, that you can add a minus r squared classical term. I think there's also a kind of a related question, which is, could this action be the classical limit of a quantum theory of gravity? So I think that's an interesting question. I don't I don't see that it's inconsistent because, as I said, the right fields and the left fields cancel. But I'm certainly like I would love to discuss that further, and I would happily send you a draft of kind of our original. I would be happy to send you a draft and get your comment on that. But for the moment, it doesn't seem that we have that problem, I guess.
Okay, let's thank Jonathan once more.